Hello, everyone. I'm going to be going over decision trees, and I'm actually going to be going over this notebook. To start, I'll have this notebook in the description of the video, so you can follow along. Yeah, decision trees. These are a really common algorithm. The next section is on ensemble methods. Let me just go over the kind of the roadmap first. So decision trees is section 34. The next section is 35, random forests and gradient boosting. These are two really common algorithms, and they're both built on top of decision trees. So you'll see a lot on like Kaggle competitions. People use random forests or gradient boosting. But you can't do those without having a good understanding of what a decision tree is. So let me first go to that Scikit-Learn flowchart. I really like this thing. I don't think decision trees are on this. Yeah, and they are not. They don't have every single algorithm. So like they have ensemble methods. Yeah, so decision trees are not on here, but do know that you can use them for classification, predicting something that is a categorical variable or predicting something that is continuous and like regression. So we're going to summarize the intuitive logic behind decision trees, solve a small example with a metric, explore the fine-tuning options in Scikit-Learn for decision trees, and then build a decision tree in Scikit-Learn. The key tool of decision trees is that some attributes provide more information than others when trying to make a decision. And we rank attributes in the hierarchy based on how useful they are. So we're going to explore this idea. So example one is when looking to monogamously date someone, which is more important, their taste in music or if they're married already. So both very important in my opinion, their taste in music and whether they are married. But if you're wanting to monogamously date someone, you're probably going to want to make sure that they are not married first. So think of that. Like we could like build just a small decision tree real quick. So we'll start with a node up here. This is going to be, say, married. Yes. No. I didn't mean to put that there. So then if they are married, then this would be don't date. And if they are not married, then we could go on to what their taste in music is. Do they like Nickelback? Nickelback's always a popular group. And I'm not trying to offend anyone on their music taste. Everyone has their own music taste. So if they like Nickelback, this is just specifically in my case. Nothing wrong if you like Nickelback. Don't date. But if they do not like Nickelback, then we could date them. So this would be a really simple decision tree. So are they married? If the answer is yes, don't date them. If they're not married, then we go on to this music question. Do they like Nickelback? Then don't date them. If they don't like Nickelback, then we can date them. This is obviously a very simple example, and if you're going to go on a date with someone, you might want to take into account more than whether they like Nickelback and whether they're married. But so yeah. So kind of the same thing when looking for someone to pet sit your cat. What is more important, how many cats they have, or how many cats have died on their watch while pet sitting? So number of cats they have, number of cats that have died on their pet sitting. For me, it's the second one. So I'm going to make another decision tree. I'm going to say more than, I think having one pet die while you're pet sitting, that, you know, that could be just an honest like coincidence, but more than one pet dying. So the answer is yes. I'm going to say no pet sit. If the answer is no, then I'm going to go into that second question. Greater than 2 cats. And the answer to this is yes. I'm going to say no pet sit. This is just one that I'm making up. And if the answer is no, that's it. So if I had like 10 candidates and I knew all this information about them, I could narrow down who I should pick to pet sit. And we're kind of going through this. So Rory is a teenager and trying to decide if he wants to go to a party, and this is the decision tree representing his process. Reply to a party invitation. Are there any girls there? If the answer is no, then Rory is not going to go. Rory, very interested in women. If there are girls there, will Miley join? If the answer is no, then he won't go. And then if the answer is yes, he will go. So it looks like this could almost, he's really, really interested in Miley, that this could just be a single tree where we just, is Miley going, yes or no? But you kind of get this idea. So there's some terminology here on decision trees. We have, this is called the root node. This right here is the root node for this. This is the root node for this tree. Then we have a terminal node. Anytime it stops, this is where, so terminal node, terminal node, terminal node, terminal node, terminal node, terminal node. And then we have child node. So that's in between the root node and a terminal node. So child node and child node. And then we also have splits and branches. So a split is anytime there's any sort of like condition where part of the data goes one direction, part of the data goes another direction. And a branch is the split plus the node, the corresponding node. So here, there's one branch right here. There's another branch right here. So now we're going to kind of look at this with data. We've done some kind of like silly examples, but let's see how we can actually use this for data. Suppose we're working on a classification algorithm designed to sort customers into 2 classes, those who pay their sales bills and those who do not. Each row in my data frame represents a customer, and I have many predictors in my data frame, including salary, total bill, club members. It's a Boolean field, and then years post-secondary education. And I apologize, I did not copy this over. So here's my data set. So I'm wanting to predict whether they pay their sales bills and those who don't. So I'm using this column as paid as my target variable, and then I'm going to make some decision trees based off this data set. So I'm going to be asking questions about the independent variables. The goal is to ask the right question in the right order so that the resultant groups are pure with respect to the dependent variable. We're going to talk about this pure. That's how we measure how well our split is. So if we do a split on something where, let's say we did a split where salary is less than, what is this, 90,000? It is less than 100,000. This would not be a great split because every single one of these rows meets this condition. And I think there's only 5 rows in this. So you want to do some splits there that actually provide value. So if we sort everyone by salary, we see that the lower salary people did not pay their bill. So that could be a potential split. We could also do, is the customer a club member? So the people that are club members, one of them did not pay, one of them did pay. So and they kind of talk about this here. Group 1 is 0, 1, 3, and 4. So these people are all club members. 2 of them paid, 2 of them did not pay. Then in group 2, we have 1 person and they did not pay. So it kind of says here this split would not be good because we'd have 2 people that did pay and 2 people that did not pay in this group 1, and then we'd have in group 2 that are not club members. We'd only have a single one, so this should be 1. So how do we decide what is the best feature? Oh, and is the customer salary less than 60,000? So if it's less than 60,000, if that's true, then we have 2 people and they did not pay, and then we have 3 people and 2 of them did pay and 1 of them did not pay. So that looks like a pretty good split right there. So there's a way to calculate this mathematically instead of just kind of sitting here and eyeballing it. And that is called entropy and information gain. So what this does is it takes the log of the probability and was able to calculate what is like how pure or how many of one category is in that group. So I have some examples of this. Yeah, how disordered our groups are instead of pure. Pure is kind of a weird term. Entropy will always be between 0 and 1. Closer to 1, the more disordered your group is. So let's kind of talk about this. So right now, before we have done any splits, what was the name of my data frame? Test. So right now, I have just a single data frame, and 2 people have paid, and 3 people have not paid. So this entropy, you use it for your entire group. So of the people that have paid, there are 2 out of 5, so 0.4 times the log 2 of 0.4. So this equation, and then minus the 3 out of 5 that have non-paid times the log 2 of 0.6. So to calculate this, from math, import log. Entropy of the whole thing is going to be negative 0.4 times log of I don't remember how that worked. I think I gotta run it to get my shift tab working. Yeah. So I have my value, and then I need to specify my base. In this case, my base is 2. So entropy of whole equals negative 0.4 times log 0.4 times 2. And then minus 0.6 times log 0.6 to the log 2 power. And I want entropy of whole, not of who. So the entropy right now is 0.97, which is pretty high. Remember, a 1 means our groups are very disordered, which makes sense. 5 instances, 3 are one category, 2 is the other. So we were going to try to use some sort of way to improve this. So now we're going to calculate entropy of a split. We're going to want to calculate the entropy of each of the groups made by the split, and then calculate a weighted average for each group's entropy. So let's calculate the entropy of a split produced by our question above for salary. And our question for salary is less than 60K. So in the true instance, so less than 60K equals true. This is going to be 0 times log 0, 2. I guess we can put a negative sign there. Minus 1 times log 1 of 2. So we run that. I don't think it's going to let me run it, but it should be 0. So log 0 of 2. Yeah, it doesn't like that. So, but the answer right there is 0. So the reason I'm getting 0 for groups 0 is there are nobody that did not pay in this group. There's nobody that paid in this group. And then there's 2 out of 2 people that have paid. So this is group 1. So I'm going to write index 2 and 0. And then for the second group, less than false. And this is index 1, 4, and 3. So in this case, there are 2 people that paid. So it'll be 2/3 times log 2, and then I want to subtract that from there's 1/3 of the group that did not pay. And I forgot I need to comment that out. So a little bit better. I forgot my negative there. But yeah, that's what I was thinking. 2/3 and 1/3. So for the second split, 2/3 versus 1/3. So it's still kind of um, um, how should I say? Disordered is the word. So now we want to calculate the entropy for this entire split. So we multiply these entropies by what percent of the data is in each split. So the first one, 0 times, and less than 60,000 is 2 out of 5, so 0.4 plus, let me save this as a variable. Split 2 false, and then times 0.6. So let's take a look at what this is. So the entire split is a 0.55. So our original entropy was 0.97, which is very high. And then by doing this split, we get a entropy of 0.55. So it's gone down pretty significantly. So for a given split, the information gain is simply the entropy of the parent group less than the entropy of the split. For a given parent, then we maximize our model's performance by minimizing the split's entropy. So you can do this by looking at the entropies of all the possible splits and then choose the split with the lowest entropy. In practice, there are far too many splits to do it practically for a person. So that's kind of where Python kind of comes in. And Scikit-Learn has an option for decision trees. I would highly recommend that you use that instead of what we kind of did. So if we take a look at Scikit-Learn decision tree classifier, there are all kinds of parameters here, and a lot of them you're going to want to tune. So there's two different algorithms. The default one is Guinea. We kind of talked about entropy. So they're both different ways to measure how disordered a split is. A lot of times you will try out both of them and see which one you get better performance on. So here, doing our split, we got a perfect score. So typically you will want to do a train and test on it to make sure that you're not overfitting. It is really easy to overfit with a decision tree because the max depth is none. So you can go as further and further down until you have groups of just a single instance. And so it's really, really high variance and low bias. And you'll usually want to set your max depth to be something. And that's called pruning the tree. So pros and cons of decision trees: they're easy to understand, they're useful in data exploration, less data cleaning required, data type is not a constraint, and it's a non-parametric method, so it doesn't assume there's a specific distribution. It's prone to overfitting, and it sometimes can struggle with cutting off splits with continuous variables. So I'm going to move on to this lab now. I'm going to kind of walk through this. This is building trees using Scikit-Learn. Use pandas to prepare the data for a Scikit-Learn decision tree algorithm. Train the classifier with a training data set and evaluate performance using different measures. Visualize the decision tree and interpret the visualization. All right, so we're going to start with importing the necessary libraries. I don't know which libraries I'm going to need right off the top of my head. I will think that I'm going to be using pandas, and I'm going to use that to start. Import pandas as PD because I have a CSV, and we'll start adding libraries as I use them. And data. All right. So it's grabbing the first row and making that the index. So I don't want that operation. Read CSV. So the default operation for the header is infer. I want to remove that so that it doesn't try to infer that the first row is the header. So I'm going to put header equals none. So now it made that. Now I want to assign column names. And I'm going to just copy and paste that. All right, variance, skewness, kurtosis, entropy, and then the class. So now we want to check for frequency of positive and negative examples in the target variable. Can do dot value counts. And you can also normalize this and get a percentage, which I like to do as well. So 55, 56%, and 44%. So not too far off. Describe your data set. All right. So what I'm looking at here, it looks like kurtosis. It might have an outlier 3 or 17.3 and 2, 6 and 12. And you can kind of look with the mean and your median, so 0.43 and 0.49, 2 and 1.9, 0.6 and 1.39. So this mean is double the median. This is pretty close as well. And then the shape of the data set. No, I don't want shape. Create, so class frequency of the target variable, that is something that I already did right up here. So create a features and labels training and testing data set. So I need to make an X and my Y. So my Y is going to be df plus my X is going to be I don't want to make a train test split, so I'm going to need a library to do that. So now I'm going to import this library in. From Scikit-Learn, import train test split. And now I want to do my split now. X test Y and Y test equals train test split X and Y and test size equals 10, random state equals 11. Oh, they want a random state of 10, so we'll do that. I sometimes mix up the orders of these, so I'll usually look at the shape of all of them. Man, I spelled both of them wrong. Shape. Y train dot shape y test dot shape. And so I made my test size 10. I want to make it 0.2. Good thing I checked that. So now I'm going to be testing on 20% of my data. Oh my God. So yeah, they already gave us this code, so I'm gonna, or no, I should have done this below, so I'm gonna move that below so I don't confuse myself. All right, so did my train test split. Now I want to do make my decision tree classifier. So this guy. So let's make our classifier dt equals decision tree classifier. And we want a random state equals 10 again. Fit the training data to do the model. So dt dot fit x train and y train. I like doing the score. This gives us your accuracy. I like to kind of peek at that first. Y train. So 100% accuracy on our training data. Let's see how we did on our test data. And 98% accuracy for our test data set. So not bad, but not always a good thing because we could potentially be overfitting. So make predictions for our test data set. Equals dt.predict x test. So cool. We look at our get params. We can see all of our parameters here. So like, let's say if, or let's do this, and then we check the accuracy. We'll check AUC, and then we'll kind of mess around with some of these parameters. So accuracy, we already checked. Then the AUC, to get AUC, first we need to make the ROC curve. So we're gonna get that. ROC curve. No, this is not it. From sklearn.metrics, import. Yeah, let's import AUC as well so we don't have to go back. AUC sklearn. and from metrics as well. And then for a confusion matrix, I like yellow brick, so I'm going to do that again. And we're not going to use yellow brick. I had to reset my Anaconda yesterday because I was having some issues with it. So we'll just use it as Scikit-Learn's confusion matrix. So cool. So let's do, we've already done accuracy. Accuracy was, we'll get accuracy again, actually. And I want test. So 98%, we want the ROC. So like, I think it's nice just being able to like grab an example. So false positive rate, we got our true positive rate, we got our thresholds. I don't need that. Y test and Y hat predict. And I don't need that because I imported in straight. And then for our AUC is so area under the curve is ROC AUC. Also very high, so that's a good sign. And then let's like do the Scikit-Learn confusion matrix. That's from metrics as well. And I don't remember how to do that. So Y true, it's true versus predicted. So Y test, Y hat test. So 149, 120. So not bad. So this time we want to do using entropy. So I'm going to do that real quick. DT. So 100% accuracy again. Let's do the same thing for our test data set. So 99.6% accuracy this time. Let's do the same thing, but I want to change the max depth because that has a huge impact. Max depth equals 3. Now let's see what we get. So now we get 95% accuracy for our train and 95% accuracy for our test. So that sets how many branches we can have in our tree. So Yeah, that's where I'm going to stop for the day. If you have any questions, feel free to reach out and have a great rest of the day. Thank you.